This is a very famous photograph, uh, which is named Lunch Atop a Skyscraper. So these construction workers from New York having their lunch at approximately 260 meters from the ground, at about 69 story. So if I'm not wrong, this is Rockefeller Center. And surprisingly, this photo was taken almost exactly 89 years back. So the photograph was taken on 20th September. Today is 18th. It's almost 89 years back that we, had, uh, we knew the prowess of what steel could do, and we could build structures that were 260 meters tall. So you already are, you must be experts in beam basics as to what is beam, how does it behave. But nonetheless, just to, give a fresh start to the design of steel beams. So beams support loads which are applied transverse, or which are applied perpendicular to the long axis of a beam. Now, how does it resist it? It resists by developing bending stresses and shear stresses. Now, if you look at the stress diagram on the right, this is the variation of the bending stress over the cross section, and this is the variation of shear stress over the cross section. Now, I know we might not have discussed this, but I'm sure you must have learned it before, so I'm not going to get into how we derive this. So what we observe from this is that the bending stress is maximum towards the extreme edges of the cross section, and the shear is maximum, or the shear stress is significant towards the center. So it is safe to say that web plays a significant role in resisting shear, and the flanges play a significant role in resisting bending. So in a typical structure with a typical framing, the beams that span between adjacent columns are called as primary beams or girders, and the beams that span between the primary beams and carry the floor loads to the primary beams are called as secondary beam or joists. Then we could have different support conditions to a beam. Now I'll just would like to draw a few sketches, so I would open this side by side with our PDF marker. I hope you can read the text in the presentation. So beams can have different support conditions. So beams can be simply supported, or they can be continuous, or they can be fixed. I'm sure you must have heard of these terms over and over the last 3 years. So now, what do we mean when we say that a beam is simply supported? Now, we already know this is how a simple support looks like. One end is pinned, one end has a roller support, the other end has a hinge support. If there's a UDL, the bending moment diagram would look something like this, with the maximum value of WL squared by 8, and the shear force diagram would look something like this. Now, what do these diagrams mean? This diagram means that in a simple support, or when there's a simple support, there's no bending moment at the ends of the beam. Okay, there's only shear force, and whatever load that you apply on this beam is getting transferred to the supports only by shear force. Okay, no bending moment. Now the beam has bending moment along its span, but it does not transfer any bending moment at the support. The entire load is transferred by shear. So this is called as a simple support. So now let us look at a simple connection. Now since there is no bending moment, there's only shear force. And we have established that majority of the bending stresses are carried by the top flange and the bottom flange, and majority of the shear stresses are carried by the web. So if it's a simple connection, it's sufficient to connect the web of the section to the column. And that is what is a simple connection. You see, only the web of the I section is connected to the column. So this sort of a section does not transfer any moment. So these flanges carry the tensile and the compressive stresses because of bending moment. Since they're not connected, they do not transfer to the support. So this is a simple connection. On the other hand, if you look at a fixed support, this is a fixed support, UDL being applied, let us say. So in this case, the bending moment diagram looks something like this. This value is WL squared by 12, this value is WL squared by 24. And here you see that at the support, there is significant amount of bending moment. Rather, the maximum bending moment. Now I'll just write these values. So this is WL square by 8, this is WL square by 12, and this is WL square by 24. So in this entire span, the bending moment is maximum at the support, and therefore here the beam transfers the moment to its support, which is WL square by 12. And therefore, in a rigid connection, in addition to connecting the web, we also have to connect the flanges. Now, there are a number of ways of connecting flanges. This is the easiest way. In this way, what is done is there's a plate. This is the I section. The I section is welded to the entire plate, and then the plate is connected by using bolts to the column support. So by doing so, we are connecting not only the web but also the flanges, and such a connection is called as a rigid connection. I mean, you don't have to know everything about connections right now. We'll look into it when we actually discuss connections. But I just want to give you, a glimpse of what a simple support is and what a fixed support is. So such a type of connection is called as a fixed connection or a rigid connection. And when you provide such a connection, you can say that the beam has a fixed support. And continuous, I'm sure you must be already aware. So whenever a beam spans continuously over more than two supports, it is called as a continuous beam. So in this case, you will experience you might expect a bending moment diagram something like this, wherein there will be bending moment at the intermediate supports. Now, if it is fixed at the support and then pinned at the intermediate supports, you will have a bending moment diagram of something like this. So there is a bending moment at all the support. That's not really the center of our discussion right now. So we should be just understanding what it means to have a simple support, which is connecting only the web to the support. What is a fixed support? Connecting the web and the flange to the support. And continuous is when the beam spans over more than two supports. So again, we have already discussed this, that for maximum efficiency in resisting bending, since the bending stress is maximum at the extreme fibers, for maximum efficiency in resisting bending, much of the beam material has to be placed as far as possible from the neutral axis, which is what happens in case of an I section. So a significant of material is at the farthest distance possible from the neutral axis, and therefore it is safe to say that amongst different types of cross sections having the same area, I section is really effective in resisting bending. So what about shear? Now, shear is to be resisted by the web. So naturally, the web area should be adequate to resist shear. So you must have, adequate width and adequate depth here, or adequate thickness of the web and adequate depth of the web to resist shear. We're going to look at how to calculate it, how to make sure that it is adequate, and so on. So, like in compression and tension members, there are again thousands of sections that you could use, as uh, uh, beam sections. But again, the most effective would be the sections whose uh, a large portion of its area is as far away from the neutral axis, and that is what happens in I sections. So this is a hot rolled I beam. So this is a beam that is manufactured in a hot rolling plant, Then we can use channel sections in exceptional cases. You can combine channel sections to form a compound section and use it as a as a beam, or you could use a wide flange beam, or you could use a hollow section. So rolled and built up eye sections or box sections are most commonly used. But even in these, rolled and built up eye sections are most commonly used as beam sections. So, what should we consider while designing a beam? Or when we say that design a beam, what does that mean? And what should we take into consideration? So there are three most important factors. First, and the most important is that the beam should have adequate strength to resist all the bending moments and all the shear forces that it is going to experience. And that is what we do. The first thing is, design the section or select the section in such a way that it has an adequate strength to resist bending moments and shear forces. Now, just before some time, we designed a compressive member. So we designed it in such a way that it had adequate capacity or it had adequate strength to resist axial forces. Here, it should have adequate strength to resist bending moment. Okay. Now, what if we need a section that would have adequate strength in axial force as well as bending moment? In that case, we would call that member as a beam column. Okay. So it's a combination of what we studied in the previous topic and what we are studying in this topic. When there's a significant axial force and there's a significant bending moment, in that case, our member is a beam column, and then we have to consider both of these things. But here we are talking only about beams, therefore it should have adequate strength to resist bending moments and shear forces. So this is the first requirement. Second, there's a stability requirement, meaning that it as as the individual elements and the beam as a whole should be stable. Now, what do we mean that by stability? What we mean is here that it should be safe against local or global buckling. Wait a minute. Are we talking about beams, right? So where does buckling come into picture? Now, we talked about buckling in compression members. Did we talk about buckling in tension members? Can you guys listen to me?
Yeah.
Yes, yes.
Is it a very difficult question to answer?
No, we did not discuss buckling in tension members.
Right? So why are we discussing buckling in beams? Anyone?
Is it because of the end they're fixed? They might buckle, maybe.
Is it because of?
End conditions if both of the edges are fixed.
So see, buckling occurs whenever there's compression. Okay. So is there compression in beams? Beams have bending and shear, right? Do beams have compression as well?
The top flange might have compression.
Mm-hmm. Any, someone else want to add anything? Okay, the question is there compression? Like we're talking about bending stresses and we're talking about shear stresses. Now, suddenly from where the compressive stresses have come into picture? Bending stresses are nothing but compressive and tensile stresses. Now, she answered it correctly when she said that, the top flange might experience compression. Yes, if it's a simply supported beam that is loaded at the top, this is a neutral axis. Along the neutral axis, the portion of the beam would experience compressive stresses, and below the neutral axis, the beam would experience tensile stresses. So this portion, that is why this is our neutral axis. There are compressive stresses here. There are tensile stresses here. So this portion of the beam is under compression. So there is a possibility that this portion of the beam might buckle, right? And that is why we talk about buckling in beams. Bending stresses are nothing but actual compressive and actual tensile stresses acting at a lever arm so that they create a moment. So these are actual compressive stresses. These are actual tensile stresses. They act at a lever arm and thereby they form a moment. and they resist moment. So we were here. That is the reason why we talk about buckling in beams. So the elements of the beam and the beam as a whole should be safe against buckling. The last requirement is stiffness. Now, it might sound a very complex word, stiffness, but simply talking about deflections, right? Whenever there are beams there, we are going to talk about deflections because that's an important design considerations. If our spans deflect, people, that are going to use the structure are not going to feel comfortable about it. Even though you say that, no, no, don't worry, I have designed this structure, it deflects, doesn't matter, it's not going to fall on your head. The moment anything starts deflecting, people start panicking. Okay, so this is not really a very good sign of structural behavior. So we have to design our beam in such a way that it does not deflect above a certain value that is designated by the code. Now, if you say that the beam should not deflect at all, that is not practically possible. Of course, it is going to deflect, but if we restrict to some values that are given by the code, the user will not experience that deflection, and that is what is important. So it has to have adequate bending stiffness to control deflection. Now, what do I mean by bending stiffness? Again, you guys should already know this, but just in case someone has missed it, this is an opportunity to revise it again. So if there's a beam that is, say, subject to a point fluid at the center, it is going to deflect, and the maximum deflection is, say, W L cube upon 48 EI. This is a formula that you might vaguely remember. Then if there's a beam that is subjected to UDL and it's simply supported, the deflection is WL to the power 4 5 by 384 EI. So this is the formula for calculating the deflection at the center. So in all these formulae, what is common is this term EI. This term EI is called as bending stiffness. The greater the value of bending stiffness, the lesser is going to be the value of deflection. So it should have adequate bending stiffness, meaning that it should have an adequate value of E. Now you will say that the value of E is always constant, which is approximately 2 in 10 power 5. That's fine. What is in your hand? You know, selecting an appropriate value of I. So it should have adequate moment of inertia such that it does not deflect above a certain limit. So it has to have adequate bending stiffness. So this term EI together is called as bending stiffness. So these are the three design considerations: adequate strength, adequate stability, adequate stiffness. Now, again, just like in compression members, there were many sections that you could choose, but which one to choose depends on a few factors. The first one is intended use. Now, you as an architect are better aware of what is the intended use of this particular structure. Okay, so based on that, you could sort of start with what type of section to choose, and then obviously economy, and then lastly is availability of the governing section. I told you before that though the catalog has hundreds of sections, but you can't really choose any because the manufacturers do not manufacture all the sections. So when get into practice, deal with manufacturers, then you sort of get to know okay, by these 5 6 sections are easily available at a very smaller cost. So this could be a good starting point for me. So these three, first is intended use. Totally depends on what you're expecting of the structure, what you're expecting of the building. Then economy and availability govern the selection of the beam section. But as I said before, I beam or a hot rolled I section or a wide flange I beam are the most commonly used beam sections. If your structure is heavily loaded and the spans are also large, so the beam sections that are manufactured, in a hot roll process may not be sufficient. There's an upper limit to this. ISMB 650 or ISMB 700 something. There's an upper limit to it. So what if you need a section that is deeper than that, and that is wider than that, and that is thicker than that? So what you can do is you can just you can just select these plates of adequate size and you can weld them together. And the resulting section is called as a plate girder. It's a beam or it's a girder that is made up of plates, and therefore it is called as a plate girder. Now this is how a plate girder looks like. So they have taken 3 plates and they have welded the plates all along. And now this is an I section that is much thicker and that is much deeper than what a hot roll section would be. So in case this is not sufficient, you can go with a plate girder. Then if you need a section for a very specific purpose, then you can also use compound sections, which are formed by combining different hot roll sections. For example, you can combine an eye section and a channel section to form this type of section. You can combine plates to form a box sections. Also, these are compound sections. Or you can also combine two channel sections to form a box section. So these are used for very specific purposes. Then the third type is castellated or tapered beams, which allow the passage of surfaces below floors. I think you already have a pretty good idea of what castellated beams are and what tapered beams are. So I'm not going to get uh, deep into this. But the prime objective is these allow the passage of surfaces below the floors. So if that is your main purpose, go for tapered beams or go for castellated beams. Then if yeah, this is how the beams look like. Here you see that they are tapered towards the support because the maximum bending moment is towards the center. So they are tapered towards the support. This is a combination of castellated and tapered. So you can pass the surfaces either from these punch holes or from these holes, or you can pass either below this tapered portion. Then the next option is if you want, the additional uh, if you want the additional help from concrete. So you could use a composite beam wherein there's a composite action. The concrete is used only in the compression side because its key strength is compression. So you use concrete on the compression side, you use steel on the tension side, and then this is a compression beam. And this is a composite beam. Another way you can use it is you can encase the beam altogether in a concrete section. The resulting beam is called as an encased beam. uh, an advantage and added advantage that you get in an encased beam is you don't need any fire treatment because there's concrete all along, and concrete provides fire resistance to the beam, so there is no need for doing any extra fire protection. So I think these are the commonly used types of beams, and depending upon what you're really aiming for, you can use any of this. So this is a composite beam. So there's beam and there's a deck at the top, or this is an encased section. So when it comes to beam selection, as to what type of section to start with, perhaps very useful for your design projects. So whenever you have a span in the range of 3 to 6 meters, you can start with angle sections. So for lightly loaded beams, but it should be lightly loaded. It should not be a floor beam. You cannot use an angle section for a floor beam. Floors are heavily loaded. So for lightly loaded beams such as roof purlins and sheet railing, you can use an angle section if the span is between 3 to 6 meters. For all the general applications and spans in the range of 1 to 30 meters, you can use a rolled eye section. For long spans that are lightly loaded, for example, industrial buildings in which the spans are long but they're not heavily loaded. For example, the roof of an industrial building. In that case, you could use castellated beams that give you a lot of depth, but you can pass your services through them. You can use castellated beams in the range of 6 to 60 meters. If the spans are long and heavy as well, such as bridge girders, in that case, you can use plate girders. That is the eye section formed by welding plates together. The span ranges from 10 to 100. Again, if the long spans with heavy loads, you can also use box girders. So box girders are heavier than plate girders because box girders have two webs. I quickly go back. Just let's consider that this is a box section. So the box section has two webs and two flanges. A plate girder has only one web and two flanges. So this will take, if the you know this might take more heavier loads as compared to a plate girder. So these are beam basics, things that you already know. You just put together the information and just uh, you know uh, for our ready reference in terms of understanding either the behavior or using it practically. So we will stop here for now. Next topic in the next lecture, we are going to look at some very important concepts, which we would start from modes of failure, and then we would learn a new theory which is called as a plastic theory. What we have learned already is called as elastic theory. We'll revise that quickly. Then we'll get into plastic theory, and then we will learn a very important concept that is called as lateral torsional buckling. And if time permits, we'll also solve a quick numerical. So That's it from me for today. If there are any questions regarding anything that we have learned so far in beams, please go ahead. Am I audible?
Yeah, you are audible.